Hello, Luke. Welcome to Lesson 70. So today we're going to be talking about probability and as kind of a subcategory to that, designated order. All right, so let's begin with probability and get your class notebook handy because there will be several definitions that we're going to have to write down today so that you can memorize. First off, let's just talk about what the study of probability is. Maybe you're already familiar with it. Maybe you've heard this term probability before. You've probably heard it in everyday language. We say it all the time. You know, what's the probability of me rolling 2 threes if I have a set of dice? Okay. So probability is simply the study of how likely something is to happen. All right. So if we have 2 dice, what's the likelihood of me rolling 2 threes? Okay, what's the probability? You can almost replace that word probability with the likelihood of something happening. Okay, so the strict definition here, the study of probability is the study of outcomes that have an equal chance of occurring. Now, a couple of key words here, outcomes, and we'll talk a little bit more in depth about outcomes later on, but essentially outcomes are the the outcomes of experiments. So the results would be a good way to say it. So if I have, let's say, a coin and I'm flipping it in the air, the outcome might be that it is heads when I flip it, or it might be tails. All right. So the outcome is the result of whatever it is that we're doing. All right. So probability is the study of those results, so long as those results have an equal chance of occurring. Those are the ones that we're interested in. It has to have an equal chance of occurring. So when we think of flipping a coin, for example, it has to be a fair coin, which means that it's just as likely to be heads as it is to be tails. Okay? There can't be any cheating involved here. All right. Same thing would apply when we roll dice. We're assuming that the dice are fair and that each side of the dice has an equal chance of showing up when we roll it. Okay, so that is what the study of probability is. It's the study of the results for equal chanced events. All right. Okay, let's continue here. So an experiment. Well, we've just kind of talked about that. When we deal with probability, each of these things that we're doing, whether it's, selecting a card from a deck of cards or selecting a marble from a bag of marbles or flipping a coin, any of one of these things would be called an experiment. Okay? That's what we're referring to in the field of probability. Okay? Excellent. So that's a fairly easy definition. All right, then we have the sample space. Now, the sample space is a very important definition. We'll be using that terminology quite often. The sample space are all the possible outcomes for a particular experiment. So let's say the experiment is flipping a coin. Okay, what's the sample space for flipping a coin? So I have my coin, and I'm gonna flip it, and I'm not gonna draw the coin picture here of somebody on this on this coin, and on the other side we might have tails, which maybe that's the Capitol building or something like that, right? Okay, so we have this coin. It could be heads, it could be tails. Those are the two outcomes that would comprise the sample space. So maybe if I were to kind of write it over here, I could say that the sample space for flipping coins is going to be heads or tails. That is the sample space. There's only 2 things in there, heads or tails. Okay? 2 outcomes. And yeah, I might actually even refer to these as outcomes. 2 outcomes. Okay? Heads and tails. All right? If I had a dice, now that's a little bit of a different story. What would the sample space be for a dice? So, or I should say a die if I've got it in singular. So here's my die, and I don't know if I can even draw anything on here, but you've got your sides, right? And I don't know, put the 1 here, maybe the 2 up on top, so forth. So you've got your dice, right? So what are the what is the sample space for the roll of a die? Well, the sample space here is going to have 6 items, right? Because there are 6 sides to a die. So we could have a 1 as an outcome. We could have a 2. We could have a 3. We could have a 4. We could have a 5. And we can have a 6. So there are 6 different outcomes. So the sample space has a size, you could say, of 6. Here the sample space has a size of 2. All right, so sample space, the size of it is totally going to depend upon the experiment. Okay? All right, so that is sample space. Now, let's talk about the probability. How do we calculate probability? All right, to calculate probability, it's fairly straightforward, actually. Essentially, what we're doing is finding all of the outcomes in the sample space that would result in an outcome that we would want, and write that as a fraction over the size of the sample space. Okay? So, for example, if I have a flip of a coin, so I have my sample space, I'll just write that as SS, sample space. For the flip of a coin, I've got 2 outcomes. I've got a heads and I've got a tails. All right? Now, if I said, what is the probability of landing a heads, okay? All right, of landing heads. What is it? Well, I would look at my outcomes and I would say, well, based on the sample size, or these sampled outcomes, how many of them, or which ones, will result in heads? Okay, well, in this case, only one, right? This one right here. That's the one that's going to give me a head, or give me heads. So therefore, I have one, outcome that will give me what I'm looking for, which is the heads. And I'm going to write that as a fraction or a ratio, comparing it to the total sample size. So the total sample size here is 2, right? So 1 out of the 2 will give me heads. It kind of makes sense, right? 1 out of the 2 will give me heads. So I would say that the probability is 1/2. Okay? The probability is 1/2. What's the probability of getting, tails? The probability of tails is going to also be 1 out of 2, right? Now what's interesting here is we have the probability of heads is 1/2. The probability of tails is 1/2. Those are the only 2 outcomes. There's 0 probability of anything else happening. And if you look, this 1/2 and 1/2, if I were to combine those, if I were to add those up, we would get 1, right? And that's the way all probability works, okay? So probabilities will range anywhere from 0 all the way up to 1. The probability of any event, whether it's flipping a coin, rolling a dice, pulling a deck from a deck of cards, selecting a marble from a bag, the probability of a given event is always going to fall somewhere between 0 and 1. Okay? 0 would indicate that the event would never happen. Okay? 1 would indicate an event that would happen every single time. All right? So what's the probability of me rolling, something that's not heads or tails when I flip a coin? Well, the probability would be 0, right? It's not going to happen. I have to get one of these 2 results. So that probability is 0. It's never going to happen. What's the probability of me getting a heads or a tails, right? What's the probability of me getting either one? Well, that would be 1. For sure, I'm going to get either one. Okay? So once again, probability is always going to fall between 0 and 1. So if someone says, oh, I have a probability of 4 of selecting the right card from the deck, that's impossible. You can't have a probability of 4. You can only have a probability that's going to fall somewhere between 0 and 1. So you could have a probability of 0, you could have a probability of 1, you could have a probability of a half or, you know, 0.5, you could have a probability of 0.263, but you could never have a probability of 4. Okay? So make sure that's clear. And if you take, you know, all of the outcomes and find the probability for each outcome. So just like we did here, we found the probability for the heads. We found the probability for the tails. Once you've found all those probabilities, they should all add up to 1, just as they did here. 1/2 plus 1/2 is 1. Because think about it, what you've done is you've just found the probability for every possible event. And so if you added them all up and they became less than 1, well, that means there's still a chance of something else happening other than the set of outcomes. Okay, which is impossible. This is our complete set of outcomes. Nothing else can happen. So they have to add up to 1. Hopefully that kind of makes sense. All right. Okay, so let's keep going. And let's try a couple. Oh, actually, before we try, we have one more thing to get through. So make sure you get this one down in your notebook too. And by the way, if you need to pause the video to write these definitions down, please do so, so that you can follow along, but not get distracted by writing down in your notebook. All right, so the last term we have to go over here is the independent event. This is an extremely important concept in probability, okay? And for right now, we're only going to be dealing with independent events. Much later in your studies of statistics in probability, you may start looking at events that are dependent. But right now, we're just looking at independent. And what does that mean? It means an event whose results do not impact future results. Okay? So, what that means would be something like this. So if I have, let's say I have a coin, and I flip the first coin, or I flip the coin, and let's say I get heads. Boom. All right, I have heads. Now I take that coin again, and I flip it again. And I get heads again. All right? And I take the coin, and I flip it a third time. And I get heads the third time. I get heads 3 times in a row. Okay? Now, is it less likely for me to get heads on the 4th try? Another way to say that, is it more likely now that I'll get a tails on my next try because I've gotten 3 heads already in a row? Well, think about that for a second. It might throw you off a little bit. Does it matter that I just got 3 heads in a row? Is that somehow going to influence my 4th toss? Well, the answer is no. All right, it's not going to influence that 4th toss. It's just as likely on that 4th toss that I'll get heads as it is that I would get tails. All right, the probability hasn't changed. All right, these first 3 flips do not affect the 4th flip, and the 4th flip does not affect the 5th flip, and so on and so forth. So if I get heads on the 4th try, well, that just means I reset and I flip it again, and I still have a probability of a half to get a heads and a probability of a half to get tails. It doesn't change. Okay? And maybe I'll get tails this time. All right? So one event does not influence the next event. We kind of reset everything after every experiment. Okay? Now, an example of something that would not be an independent event would be something like, let's say I have a deck of cards, okay? And I randomly, without looking, I just pull a card out of the deck. And let's say I pull, the Jack of Hearts, okay? I pull out the Jack of Hearts. All right? So now he's out of the deck, and I set him aside. All right, and now I'm going to repeat the experiment. I'm going to pull another card out of the deck. Well, now, what are the chances of me pulling out a Jack of Hearts on my second draw? Well, if it's a standard deck, the chances are 0, right? There's only one Jack of Hearts in the deck, and I already drew that out. So my first experiment, I had a potential. I had a probability of picking out the Jack of Hearts. If you think about it, there are 52 cards in a deck, right? And one of them is the Jack of Hearts. So I have a probability of 1 out of 52 of selecting the Jack of Hearts. Okay? For my, this will call this our first experiment. All right? Our first experiment, we have a probability of 1 out of 52 of selecting the Jack of Hearts. And I dig in, I pull out a card, and lo and behold, wow, it's the Jack of Hearts. And then I set him aside, and then I do my second experiment, right? And now I can say, well, what's the probability of me pulling out the Jack of Hearts again? Well, the answer is 0, right? Absolutely 0. There's no chance whatsoever because I already pulled out the Jack of Hearts and it's no longer in the deck. Okay? So here's an example of where our first experiment impacted our second experiment. Okay? Because we pulled out the Jack of Hearts in the first one, it was not at all possible to pull it out in the second one. All right. So if in the second one, I pulled out the 10 of diamonds, well, then that would mean that for my, if I had a third experiment, my first and second experiments both will influence my third experiment because now it's not going to be possible to pull out a 10 of diamonds. All right. So these would be examples of dependent events. Okay? And these can be kind of complicated when we start trying to find out the probability of things. All right? And that's why generally we don't look at these events first. We look at instead independent events. But watch out because they will try to trick you with these. Okay? Because sometimes we feel like, if I flip a coin 4 times in a row and it's heads 4 times in a row, there's kind of this intuitive feeling that, gosh, this 5th time it's got to be tails, right? We couldn't have 5 heads in a row. It just seems so unlikely. So we begin to think that it must be more likely to flip tails on my 5th try. But actually, that's wrong. It's not more likely. It's equally likely to flip another heads. Okay? All right, so bear that in mind because that is very important. They will try to kind of trick you on these. All right, so let's move on. Let's try a couple here and see how we do. Let's kind of put some of what we've talked about into practice. So let's say you have 2 dice, all right, and they are rolled. All right, what is the probability that the sum of the numbers rolled is 7? Okay, and actually, you know what? Before I do this, I'm going to start with a simpler one. I'm going to say, let's say I have a single dice, okay, a single die. And let's say I want to know what's the probability of rolling a 4. Okay, what's the probability of rolling a 4? Well, in order to find the probability, remember, we need the sample size. That's always the denominator. Okay. And then we need, we'll call it the desired outcome out on top. All right. What is the desired outcome? So the first step in these probability problems is always to figure out your sample size. That's so important. It's really the first thing to do. I might even write that. Step number 1, find the sample size. Find the sample size. Okay? So if we have a die, what's the sample size? Well, it's again the 6 sides of the die. So the sample size or I should really say the sample set is 1, 2, 3, 4, 5, and 6, right? And actually, I'm going to even change that. I think that makes it a little bit more clear. Find the sample set. All right, this is our sample set. This includes all of the outcomes for this particular experiment. All right, now, what's our desired outcome? Our desired outcome here is 4. And there's only one way to get it, right there. Okay, so therefore, there's one way to do it. So we put the 1 in the top. And then what's the sample size? Well, the size of the samples, the sample set, is 6. There are 6 things in there. So the probability of rolling a 4 is 1 out of 6, or 1/6. Okay? So that is how you'd find the probability of 4. What's the probability of 3? Well, it'd be kind of the same logic. There's only 1 3 in here, so we have one outcome that gives us a 3 out of the 6 outcomes, so the probability is 1/6. Okay? But we could get a little more creative here. What about, what's the probability of something greater than 3? The probability of rolling something greater than 3. Now, this is a little bit of an interesting question, because if we look at our sample size here, or our sample set, we'd have to find all of the outcomes that are greater than 3. So 6 is greater than 3, 5 is greater than 3, and 4 is greater than 3. So we have 3 outcomes that are what we're looking for. They're the desired outcomes. There's 3 of them. Okay, so that is the numerator. We have 3 possible outcomes that are what we're looking for, out of how many total outcomes? 6. Now this can be reduced just like any other fraction. So 3/6 is going to be 1/2. Now sometimes we'll even write these as percentages. You'll often see probabilities written as percentages. So 1/2 as a percentage is 50%. So you might say we have a 50% shot of rolling something greater than 3. Okay? Excellent. All right, now let's go on to this next one here. 2 dice are rolled. What is the probability that the sum of the numbers rolled is A, 7, or B, a number greater than 8? All right, well, what's the first step again? We always first look for the sample set. Okay, so what's the sample set here? Well, this is kind of interesting because we have 2 dice that are being rolled, and we're trying to find the sum of things. So we've got lots of different things that could happen here. I could roll a 1 with the first dice and a 4 with the second dice. I could roll a 3 with the first dice and a 6 with the second dice. There's so many different options here. So we first need to list all of those options, okay? And to do so, in this particular case, I think it would make sense to do it more as a chart. I think this is what they do in your textbook as well. So let's say, as a chart, what are the possibilities here? And actually, let's see if I can't just make this a little nicer. Something like this, maybe. And something like this. To try to make a little, a little graph here, or a chart. Yeah. Can I? Well, something like this anyway. It's kind of messy. Okay, so there we go. Maybe we'll just do it this way too. 1. Okay, it's rough, but there's my chart. So let's say that on our dice, again, it's a 6-sided die. So we have for one side, or for one dice, we have the possibility of rolling a 1, a 2, a 3, a 4, a 5, and a 6, right? And then for the other dice, we also have the possibility of rolling a, um, let's see, I'll put it over here. A 1, a 2, a 3, a 4, a 5. Oh, I'm short. We're going to have to make one more row here. It's getting a little messy. But I think you'll be able to get the idea. A 5 and a 6. All right? So, again, think of this top row representing whatever, the first dice gave us. The first dice. And then we have the second dice. So, top row, first dice here. And then the side row is going to be this dice, or this die here. Okay? Now, what would the sums be? So, if I roll a 1 with one die and a 1 with the other die, what we're interested in is the sum. So 1 plus 1 is 2. That would be the sum. If I rolled a 1 with the first die and a 2 with the second die, my sum would be 3. A 1 and a 3 would give me 4. A 1 and a 4 would give me 5, 6, and 7, right? So those are the only possibilities that I could get with my first dice being a 1, all right? And then if my first dice is a 2, the possibilities would be a 2 and a 1, which would be a 3, a 2 and a 2, which would be 4, a 2 and a 3, which is 5, and again, they just count up, all right? And then with a 3, well, now the possibilities are 3 and 1 is 4, 5, 6, 7, and I think you get the idea here, 8 and 9, 4, if I roll that, then I could have a 5, a 6, a 7, an 8, a 9, and a 10. And then this is going to be so on and so forth. And this is going to be 8, 9, 10, 11, and 12. Okay? So these numbers in black here, they represent all the different possible outcomes for our experiment. All right? This is the sample set. Okay? So what is their question? They want to know what's the probability that the sum is a 7. Well, to answer that, remember we're going to have our fraction, and we need to have all of the outcomes that give us the desired outcome, which in this case is 7. So looking at our chart here, which ones give us 7? Well, we have a 7 here, so that's one outcome that gives us 7. Here's another outcome, and another, and another, and another, and another. All of these different combinations, if I roll a 6 and a 1, that would give me 7. If I roll a 5 and a 2, well, that would give me 7. And a 4 and a 3, well, that would give me 7. So there are multiple ways that I could get a 7. In fact, there are 6 different ways of getting a 7. So we would write 6 in the numerator because that represents those 6 different ways. In the denominator, we need to look at how many outcomes there are in the sample set. So how many are there total? Well, we have a chart here that's got, 6 up on the top and 6 along the side. So I can find the total number inside by taking 6 times 6. So there are 36 different outcomes here. So my probability is going to be 6 over 36, which, of course, can be reduced to 1/6. Okay, another way to think about this is if I roll these 2 dice 6 different times, in a perfect world, one of those times I would get a 7. That's another way to think of these fractions. If I roll them 6 times, in a perfect world, one of those times I would get a 7. All right? Okay, very good. Now, how about B? How about a number that is greater than 8? Okay, well here we need to find everything in this sample set that produces something greater than 8. Okay, so if it's greater than 8, it can't be equal to 8 either. So the way it kind of works out with this chart is all of these 9s, of course, would work, and the 10s, of course, would work, and the 11s would work, and the 12 would work. All of those outcomes would be something that's greater than 8. So how many are there? Well, there's 4, 7, 9, 10. There's 10 red circles here. 10 possible outcomes that would give us something greater than 8. So that is our numerator. And then our denominator, again, is just how many there are in total. There are 36. This could be reduced to what? 5/18? 5/18. Which again, another way to think of it is if I were to roll these dice 18 different times, in a perfect world, 5 of those times I would have something greater than 8. Okay? Which would then also mean that, 13 of those times I would have something that's not greater than 8. Because 18 minus 5 is 13, right? So 5 out of 18, I get what I want. 13 out of 18, I don't get what I want. So I actually have a better chance of getting something that's not greater than 8. And that makes sense. If we look at our sample set over here, there are these red circles, but there are a lot more that are not red circles. So we have a much better chance of not getting something greater than 8. Okay? Excellent. All right. Moving on. One more thing we need to talk about in relation to probability. And that is, what about if we want something in a designated order? So everything that we've looked at so far has just kind of been a single event. We're interested in deciding whether or not we're going to get a heads, or we're interested in whether or not we're going to, pull a certain card out of a deck, or interested in whether or not we're going to roll a 7. Okay? But sometimes we want to predict how likely a certain set of things could occur. So, oh, that's a typo there. Designated. So, the designated order. Okay? So, for example, let's say I know that if I have a coin and I flip it, the probability of getting heads is 1/2. Okay? Probability of heads is equal to 1/2. Okay? But what's the probability of me getting a heads, and then a tails, and then a heads, and then a tails? Okay? So in that order. So now, not only am I looking for, getting heads, but I also am looking for what's the probability of me, doing this 4 different times and getting these exact results. A heads, a tails, a heads, and a tails. Okay, what is the probability of that? All right. Now to know this, there's a rule here. Okay, and that is it's a multiplication rule. So if we're looking for something in a designated order, and we want that order, we would find the probability for the first event, multiply that by the probability of the second event, multiply that by the probability of the third event, and multiply that by the probability of the fourth event. Okay? That's how we would find the probability of all of these events occurring in the order that we've given it here. So what's the probability of the first event, heads? Well, we already said that. It's 1/2. What's the probability of the second event of getting a tails? Well, that's also 1/2. So we're going to multiply 1/2 times 1/2. And then what's the probability of getting heads again after that? Well, it's 1/2. And the probability of a tails is 1/2. So the probability of getting a heads and then a tails and then a heads and then a tails is 1/2 times 1/2 times 1/2 times 1/2, which is 2 times 2 is 4, times 2 is 8, times 2 is 16. So it's 1 out of 16. So again, you could think of that as you could try this experiment 16 different times, and in a perfect world, one of those times you would have a heads, tails combination. Okay? That's what that means. And it does actually make sense. I know that, it's easiest just to take this on faith, that when we have multiple things that we're trying to find the probability of, in a certain order, we simply multiply their probabilities by each other. But it does make sense because if you think about it, so the first scenario, let's make it a little bit easier. Let's say we've got a heads and then we want a tails. So we just want heads, tails. Okay. Well, what could happen? All right. If this is what we want, what could happen? Well, I could flip the coin and I could get a heads on the first try, which is great. All right. Now, on the second try, I could get another heads. So I could end up with a heads-heads combination, right? On the other hand, if I flipped a heads first, I could flip a tails on the second try, right? And those are the only two things that could happen if my first try is a heads. Then my second try is either going to be a heads or my second try is going to be a tails. I'm going to end up with heads, heads or heads, tails. On the other hand, if I flip my first coin, my first try, and I get a tails, well, then my second try could be a heads. Or, again, if I flipped it and got a tails, my second try could be another tails. And that's the only two possible outcomes for when I flip a tails first. Okay? And if you think about it, these are the only four possible ways that something is going to happen, right? I'm either going to end up with heads, heads, or I'm going to end up with heads, tails, or tails, heads, or tails, tails. Try to think of another combination that I could potentially end up with, and you won't find anything. All right? These are the only four things that could happen if I'm flipping the coin twice. So if my question is, well, I want to know specifically what's the probability of this combination, a heads-tail combination. Well, if I look at my sample set over here, because again, this is my sample set, these are all the possible outcomes. The only one that produces a heads tails is this one right here. Okay? So I have 1 out of, what's the size of the sample set? 4. So I have 1 out of 4. So the probability of getting a heads tails is a 1/4. Now, if I go back to our rule of multiplication, we'll see how this works out. So if I have the heads, what's the probability of flipping a heads? It's 1/2. What's the probability of flipping a tails? It's 1/2. So I have to take 1/2 times 1/2. And what does that give me? 1/4, which is exactly what we got right here. Okay? So this does actually work. Okay? If for this example, I did the experiment 4 times, so I'd have to go through all the possible outcomes. If I started with a heads, I could get a heads, tails, 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 or I could get a heads, tails, tails, heads, or I could get a heads, tails, heads, heads, or I could get a heads, heads, tails, tails. Okay? And that would be all 4 possibilities for when I get just a heads at the first, flip. Okay? And then I could continue and say, well, what happens if I get tails? And eventually I'm going to end up with, 4 columns here, each having 4 in them. I'm going to end up with 16 possible outcomes. And that's where this 1 out of 16 comes from. Okay? So hopefully that makes sense to you. All right. Excellent. And I think that is where we will stop today. I don't want to go too long here. But essentially, this is just an introduction to what probability is and how to find it. Watch out. I would say the trickiest part to this whole thing, maybe 2 things. One is remembering that if you have a designated order of events, where we're really asking for what's the probability of this event happening, followed by this event, followed by this event, followed by this event, then you simply multiply the individual probabilities of each event. Okay? You have to remember that. The other thing that can be a little bit tricky is the idea of the independent event. Watch out for that. They're going to try to confuse you They're going to say, all right, if I flip a coin and I get a heads, and then I flip it again and I get another heads, and I flip it again and I get another heads, what's the probability of me flipping it a fourth time and getting a heads? And the answer is simply 1/2. It's the same probability as it was every time you flipped that coin. All right, it doesn't matter what happened previously. The probability is going to be the same because it's an independent event. We reset everything at the beginning of every experiment. Okay, very good. So we will stop here for today. Good luck on your seat work, and I will see you in the next lesson.